good day, a second time. Welcome to the second installment of my video lectures. Hopefully my face is still powdered nicely and you are still looking forward to have some very exciting stuff that I can discuss. So remember that we are at this moment we are discussing data types. So during the first week of classes at the university, I presented them in class. I discussed how you would create data types. And then in the first video lecture that I've presented, I've shown you how you would create data types. And I think I've just said something wrong here. In the first couple of lectures, I've shown how you can use the data sets that someone has created for you. And then I've discussed how you can create them in the previous lecture. Now today and in this lecture I'm going to continue and discuss how you would create your own data types at the end of another example. Hopefully after you've seen this example you will have enough knowledge to go and create all the data types to write the next big program. I don't know what you want to write, but the next big program that will make millions of rands of dollars. And so let's continue. So I'm going to work within the field of complex numbers, and that's sort of the next example that we want to discuss. Now complex numbers are a strange thing sitting there. Some people also refer to them as imaginary numbers, but I don't think there's anything imaginary about them. And maybe I should also tell you, of course I can't go in all the detail about complex numbers. That is something that you will discuss during your lectures in mathematics at some point. I'm sure you will do that. The only thing I can say about complex numbers is when I first saw them in my mathematics class, I mean, they are just plainly beautiful. I sat there, I almost wanted to cry. I did not cry, I mean, you sit in the first year class, or is it second year? But they are just pretty. So I hope that I can that will probably be the first time that you hear about complex numbers. You will do them more formally in mathematics, certainly at some point. And when you get at that point, maybe you should think about me and know how much I like complex numbers. I think they're pretty cool. So let me do this at the end of examples. So a complex number, say z, consists of two parts. It consists of real part and then a so-called imaginary part. So x is the real part and y is the imaginary part. And x and y are just normal integers. So for example, 3 plus 2i is a complex number, or 42 plus 42i is another complex number. So they're just complex numbers. And once you have these complex numbers, you can do all sort of operations on these complex numbers like you would do with normal numbers. So let's, for example, have the number a equals 3 plus 4i. And I have a number complex number b equals minus 2 plus 3i. So I have two complex numbers over there. Now the one thing I can do with numbers, I can add them. Now I'm not going to discuss the rules and all the things for this algebra to work out here in detail, but you can get the formulas in the book, and when you discuss complex numbers in mathematics at some point you will also learn about them. But if I add a plus b, I basically add the real parts together. So in this case 3 plus minus 2 would be 1, and then 4 plus 3 would be 7, so the result of that would be 7i. I can also multiply complex numbers, so a times b, and how you would multiply is you multiply this by this, you multiply this by that, multiply that by that, and you multiply that by that. So 3 times minus 2 is minus 6, plus 3 times 3 is 9, and then I keep the imaginary part, so it's 9i, and then I have 4 times minus 2 is minus 8, so I have minus 8i, and then I have 4i times 3i. Now this is where things get really nice and interesting, since of course that's 12. But the interesting thing about complex numbers is that I times I is equal to minus 1. So in other words, 4i times 3i is equal to minus 12. And then I just have to add all these things up. So what do I have over there? Minus 6 minus 12 is minus 18, and 9 minus 8 is 1. So plus I. So a times b, where a is this number, b is that number, is minus 18 plus I. You can go in the textbook. I actually have the textbook over there. If you look there, for all these numbers, it's a bit small on the screen, but you can look on the textbook on page 390. There's actually some formulas in general for any kind of operations on a complex number. For example, addition, multiplication, magnitude, and then the two other things that you usually do with a complex number is to get the real part and to get the imaginary part of a complex number. So page 390, and you will get the general formulas. Let me maybe do one more thing. If I want to calculate the magnitude of a, that would be the square root of the real part, so that would be 3 squared plus the imaginary part squared. So 4 squared, that is of course 25, so the answer is 5. When I write this mathematics out, I feel a bit like William Smith. Is that the guy who did all the mathematics on television and then write, and then he has all these things. Now I just have to write there and start scratching my face. I think it will be funny. Okay, that's not the point. So why do I want to do complex numbers? Well, complex numbers have a bunch of important applications. Of course, they are nice. That's the first thing. But they play an important role in electric circuits. If you do signal processing in Fourier analysis, they are really, really important. In fact, if this video that will be compressed at some point, will probably do at some point with the compression algorithm some Fourier analysis, either for my voice or for the video. And for that Fourier analysis to work out, the analysis to understand, you will need complex numbers. In control theory, you will use complex numbers as well. Remember, control theory is something that, for example, in a car, to make sure that you don't, if you have ABS or something and you press on the brake, that it makes sure that it doesn't go off the road and you brake properly. There's a concept of Laplace transforms, and they are also nicely understood with the aid of complex numbers. So actually, complex numbers, even though they have this imaginary part of them, there's nothing imaginary about them. They exist everywhere. And so we use them. But if you look at Java, you will see that Java provides primitives. Well, they provide the normal integers and the doubles and floats and all those things, but they actually don't provide any support for complex numbers. And therefore, we would like to have that, and now we have all the tools to create them. Remember, although Java does not have a complex number at this point, it does not mean that it can't have a complex number, and that's the whole point of creating data types. You define your own data types, and in this way Java can have a complex number, although you have defined it. So let's assume for the moment that a complex class has already been implemented by someone. So in other words, someone defined, it just mysteriously existed and came into being. Then of course what we want to do is we want to have something such as create a new complex number. So A is a complex number, new complex, and I specify the real part and the imaginary part. Just look how that resembles the normal way we define values or the normal way we define numbers in Java. So remember, in Java we would have said int x, and then int x would have been okay, we would not use in the case of the primitive types new, but you would give it a value, and the value would be 42. And now in the case of the complex numbers, I can do something such as complex z equals new complex, and then I give a real part and an imaginary part, and so this will represent the number z equals 42 plus 21i. As a side note, I want to sidetrack at this point. in Java you have primitive types, but sometimes you want to have an object representation of a primitive type. Remember, a primitive type is not an object. And so the way to do this, for each primitive type there's actually a Java class with the same name starting in capital. So you have the integer class, and that would be the object representation of this primitive value. And you will also have double and float. That is just a side note, maybe something you can look into. Okay, so but I'm here with the complex numbers that I have, so I can create a complex number like that as I have on the screen there. And then I can have something such as complex number C is equal to A times B. Note there's no reason to say new complex number, since A times B will return a complex number. So something else to see that things can return. And then I can print them out. I can print out A, B, and C. And remember, A is a complex number, so its type is a complex number. But since I print it out, I want to use a string representation of it. Java will automatically call the .toString method of this class. Let's just look a bit at this line of code there as well. So I write down A dot times B. And this is sort of the object-oriented way of doing things. You could also, when 2 or 3 months ago, without the knowledge that you have had now, you would have written something such as complex dot times and then do A and B. But what we do now here is we say that A is a complex number and it will know how to multiply itself with another number B. Okay, so let's look at the implementation of this complex class then. So what I have over there is class complex, and remember we have the instance variables. That's always the thing that we start with. And in the case of a complex number, it should be clear what the instance variables should be. They should be the real part as well as the imaginary part. And so I have them there in the code as well. I have the real value and the imaginary value. I make them final. So in other words, these values cannot change over time. Then I have a constructor, and this constructor basically sets the real part to whatever the client code is providing, and it sets the imaginary part to whatever the client is providing. ToString should not be difficult to understand, app should not be difficult to understand, but let's look a bit at this code for plus. So remember, I would have written something such as A dot plus B. And so A is a complex number and B is a complex number. So we have all these things that's now part of this equation. Now if we look at this code and I go back to that, you will see that the real part is now of course equals to the real part of A, since remember, if I'm in this object, in this code over here, RE refers to the real part of the current instance that I'm working with. And if you look at the example here of A plus B, then the RE will refer to this object's real part. So the current object that I'm working with. So RE there is referring to the A, if I use this example. But now of course I have to add the real part of the other object that I want to add. But now you can't just write RE down, since RE would then of course refer to A, this A that I have over there. So RE refers to this A, and if I just write down RE plus RE, I just add A to itself. So to get this right, I'm going to write code RE plus, and then I'm going to specify that I want B, this object's real part. So B.RE. And then I add them, and so I add their real parts and their real parts together. And then of course similarly for the imaginary part. And then, interesting enough, then I create a new complex class of this result of this addition, and I return this. And now you can see that I can actually return real and some other objects, as if they were just a primitive type. Times work in the exact same fashion. I'm not going to go through it, that you can do as homework. Just one thing to note here again, when I say b.re, I can access the instance variable because I am in the complex class. However, remember, if I'm a client of complex, then I don't have access to these instance variables. Then I will have to make another plan. But that's something that I will get back to at some point when we discuss chapter 3.3 and I discuss how we will define define our own APIs or our own data types. Well, we define that as how we define APIs. Okay, so now you can work with complex numbers. And what I'm going to do for the rest of this lecture is to use the idea of a complex number and then use an example. And then you will see how nicely they fit together. And the example that I want to use is the so-called Mandelbrot set. They are fractals. They are really fascinating. Do yourself a favor and go and read the Wikipedia page of the Mandelbrot set, or maybe even read more on that. I mean, they are fascinating. They are really nice models. They allow you to model, for example, clouds, contours of mountains, the winding of riverbeds. They also play a useful role in image compression. They are, of course, so beautiful that they play a role in art as well. So what I want to write is a program that can generate these Mandelbrot sets. Now, what is a Mandelbrot set? Well, a Mandelbrot set is a set of complex numbers. And we have the following rule. So we plot xy as z, as black, if the complex number associated with this position xy, in other words, the complex number z plus x plus yi, is in the Mandelbrot set. Otherwise, we would plot a white point. I repeat. So we start with a grid of points, or we start with, it doesn't have to be a grid of points, we start with a bunch of numbers. So then the pixel or at position xy is black if the complex number x plus yi associated with this xy position is in the Mandelbrot set. Then it will be black. Otherwise, I would make it white. Now the question, of course, is, I've just redefined the problem. The question is now, of course, when is this point x, y, or when is z in the Mandelbrot set? And the thing is, there's no simple formula to do so, so we have to use an algorithm. And the question that I want to answer now is z0 in the set? And how do we do that? What we do is we calculate this series. So we start with z0 and then we calculate zt plus 1 equals to the previous z, or the z squared plus z0. And we do this many times. Now, if the magnitude, the absolute value of zt diverges to infinity, then z0 is not in the set. Otherwise, z0 is in the set. So, for example, I have here an example where t is 0. I start with this number half plus 0i, and I calculate this now many times, and then I see it actually converges. So, in other words, this number is in the set. I start with another one, and I do the same thing, and I see this number just grows and gets bigger and bigger and bigger. So, this one is not in the set. So now I have a way of saying that a number is part of the Mandelbrot set or not. Now, of course, this is actually defined for all the positions that I have there. But of course, there are infinitely many numbers that you can work with. So we can't really implement this for all infinite many numbers. And of course, to show that it's actually converging to a number is also a bit of a problem, since how long do you have to iterate before you can say that it actually converges to that, or that it actually diverges? Maybe at some point it will converge, or maybe at some point it will diverge. So we have to find some sort of trade-off here, being able to do so. So we want to solve these practical issues and implement this. So what we're going to do is we're going to start with a grid of points, and I'm going to specify a position in where this grid should be centered. So in other words, I give you a XY position there, and that would be the center of the grid, and that could be anywhere in this Mandelbrot, in this world of XY positions that I can have. And then I will sample n values around that. So I will have an n by n grid of points centered around a certain point. Now there are two things. It's a fact that if the magnitude of zt after you've iterated a couple of times are bigger than 0, then z is not in the Mandelbrot set. However, if you've iterated many times and after 255 iterations is still less than 2 the magnitude, then z is most likely in the Mandelbrot set. So the previous one is a fact, the second one is sort of a rule of thumb. We can't guarantee that it will not diverge at some point, but we believe that it will actually converge, and so it is part of the set. So now I have all these things at play, and let's see if I can use them usefully. So in other words, I want to write a function that will answer the question, is Z0 in the Mandelbrot set? So how will I do this? Well, I give a Z0 as the complex number over there, and then I'm going to iterate, do that sum. Remember, if I go back to the slides, what we're trying to calculate is this value there, zt squared plus z0. That is what I'm trying to calculate. I iterate over that. So let's go to the code again. So for t equals 0, t less than 255, so we will try 255 times. So if z's absolute value is greater than 0, then we know that this number is not part of the set. So we will return white. So we say just draw white. So remember, we're trying to draw the Mandelbrot set, and white means it's not part of the Mandelbrot set, black means it is part of the Mandelbrot set. So let's go back to the slides. So I have over there that if the absolute value of z is greater than 2.0, then I return white. Otherwise, I make z multiplied by itself and I add z0, and I do it again. So this is the step of z squared plus z0, and then I try this 255 times. If I've tried this for 255 times and it's still not greater than 0, so it's still less than 0, then I assume it's part of the set, so I return black. Otherwise, I would have returned white at some point. You could, of course, make it a bit more interesting by not returning just white, but maybe a grayscale value associated with how many times you have to iterate before you get to this, before you realize that it's actually diverging. So then we live in this gray world. Okay, and now with that to our disposal, we can actually implement code to plot a Mandelbrot set. So this is client code, and we will use the complex numbers again. Well, the complex number was of course used in the previous slide there as well. And remember, with this code, it would have been possible to write that and implement that without using a complex class. But then you would have to written for every time you use z times x, z, you have to implement that full formula, and you will have to keep track of all the x components and the y components, or the real parts and the imaginary parts of a complex number. Okay, so let's see what I do there. So xc and yc is the center of the Mandelbrot set. So here imagine that you have this infinite, well, you can imagine that if I have this if this there's some interesting things there. So imagine this is then my space of all the numbers. Then I'm interested to look maybe at this particular part. So these are all numbers, this white, and then I specify this xc and yc. If I look at the slides, look there, this is the xc and the yc. In other words, that's the center of the place where I'm interested to plot this thing. Of course, if I go back to my whiteboard, you will see I can specify it many places. I can see and maybe do it over there. So I can specify xc, yc over there as well. And then, of course, I take a grid around this with a certain size, and that is the one I'm going to plot. And hopefully that will be interesting. So the size is how big I want to have it, and then of course I make a picture. In this case I just make it n by n, and I really want you to do as homework, look at these two lines and make sure that you understand what's going on. Basically what it does is the aim is to sample an x0 and a y0. So in other words, you get the corresponding starting point, this z0 to start with. So you will see x0, y0, and then I create a complex number z0. And then once I have that, I can call this function that I've written before. Remember this Mandelbrot divergence function, and it will return white when it's in the set, otherwise it will return black. So if I go back to this code, I do this again, and then I have the color there, and then I set the picture at position I, and remember the picture's coordinate is not the same as the world that we're living in this Mandelbrot set. I set the color just to make this concrete again. Remember that in this framework, x is running in this direction, y in this direction, and this is 0, 0. But in the case of the picture, this is 0, 0. And so we calculating the points over there, but when we set the color, we have to just flip it around so that we actually set the right coordinate. Again, that's homework. So you have, for this particular slide that I have over here, you have two things to do as homework. You have to make sure you understand why I write down x0 is this formula, y0 is that formula. And then once you do that, you can do that and you get all these nice pictures. So for example, here I have the Mandelbrot at -5 and 0, and then with that size. And there's another place I can zoom in. You can look in the internet and Google for Mandelbrot set. I've said that before, and you have all sort of pretty pictures that you can find about Mandelbrot set, also with videos that zoom in. I mean, you can imagine, I've said there are infinitely many numbers sitting there, so you can zoom and they fly around through this fractal, and it's really fascinating to just look at it. Okay, so that brings me to the end of this example that I want to discuss. And that also gives me some time to wrap up things. So in the past 2 lectures, what I've done is I've shown you how to create your own data type. So in other words, at this point, you are able or capable of using someone else's data type. So there's someone who wrote the code for you, and then you can use them in your own client code. You should be able to understand that. And the second thing that you can do at this point is you can actually implement your own data types as well. So if the concept is not part of the Java language, then you are capable of implementing yourself. And what you're actually doing is that you are actually extending the Java language. So what is the purpose of this data type stuff? Well, it gives you the opportunity to simulate the real world, physical worlds. So you can have things for a charged particle. That is what we've discussed. I haven't done a molecule, but you can think you can do that. You can have code to implement the student class to do that. And it is not necessarily always easy for this model to reflect the reality. but it definitely gives you some abstraction power to do so. And next week, when we discuss how to design your own APIs, we will touch a bit more on this as well. And the other important thing is to realize that what we've done now is that we've given Java a complex data type. Java now can handle matrices, polynomials, vectors, and all the things that is at your heart's content. I do thank you for listening to me. Next week, as I said, we will look at designing APIs. We will do 3.3, and we will do another example of simulating bodies. Until next time, goodbye and have a good time.